ಓಯ್ ಒಂದು ಸಾಕು ಸ್ಲೋ ಮಾಡಿಬಿಡ್ರಿ. ಅದಲ್ಲ Okay, so good afternoon friends. So today we are starting with polymers. So in our earlier class we have discussed about this polymers and types of polymers. This is just a quick review. So as we are aware, polymers are the material which are used for all the general purpose applications. Earlier era was brought into Stone Age, Iron Age, Bronze Age, and then Polymer Age. Okay, so now let us see about the polymers. So polymer is a Latin or Greek word where it is split into two. Poly means many, mer is a molecule. Okay, so it is called as a single molecule is called as mer or monomer. The series of these monomers or mers is called as polymers. So every polymer has a structure. So this structure is nothing but the arrangement of atoms in case of the metals or in the solids, and here in case of polymers it is the arrangement of molecules, and these molecules are in the form of macro in size. Hence these are also called as macromolecules. And the arrangement of these structures, the arrangement of these polymers are called as macromolecular structures. So now, what are the general structural and chemical characteristics of a polymer or the molecules? So this arrangement of polymers, okay, in a particular order, the structure decides the strength of the property of the polymers. So based on what is this, a cross link, whether it is a straight and the bonding or a chain, blocks, based on this arrangement of structures and the chemical bonding between these or the reaction between these individual monomers, okay, is dependent on the structure. So what are some of the common polymeric materials and how they do differ chemically? Okay, so what is that process, how each polymer changes chemically, that we are going to see. How is this crystalline state in a polymers are different than in metals and ceramics. So as we have discussed in earlier classes, that metals are crystalline in structure, ceramics are non-crystalline in structure, whereas these polymers are coming in between the metals and the ceramics. So ceramics are non-crystalline, metals are crystalline, hence this comes in between these two, that is called as semi-crystalline. So this semi-crystalline is nothing but it's a combination of metallic and ceramic arrangements. So here some of the polymers are can be converted to crystalline, and some are in the combination of non-crystalline. So according to the need and applications, by the degree of polymerization, we can try to control the crystalline structure, but however it is little bit difficult and more complex. So these are the polymeric structures. Now you can see here a single ethylene. So ethylene is the most common used polymer. Now you can see poly means many, mer means it is repetitive unit, as we have seen in earlier. So now you can see this one polyethylene, that is C2H4, is being considered a single monomer. So monomer, and this is repeated. So then it becomes a chain. So chain of what? It's a carbon chain. So these are the carbon, these are the hydrogen. So the repetitive unit or the repetitive building blocks of ethylene is called as the polymers. Okay. Now you can see this is a polyethylene, this is PVC, and this is polypropylene. In each type of polymer, you can see there is repetitive blocks, either it is a polyethylene or a polypropylene or a PVC. So in this you can see, in polyethylene, the carbon and hydrogen molecules are repetitive in nature. Now, whereas in the PVC you can see the C2, H3 and Cl. So this is one molecule. So like this it is being repeated. That is C2, H3, Cl. So here two carbons of two molecules of carbon, three molecules of hydrogen and one molecule of chlorine. So this is being repeated every time. Now you can see in case of polypropylene. So C3 and H3, this is repeated again and again. So there are three hydrogen molecules and three carbon molecules. Okay, and the combination of hydro. So this is being repetitive in nature. So each one is called as monomer, and this monomer is being repeated again and again. Hence you can see in all the type of polymers, that is polyethylene, PVC and polypropylene, or in any other type of polymers where it is repeated. And the process of repeating this, okay, and there should be proper bonding in between these molecules, is done with the help of polymerization process. So this polymerization process is nothing but it's a arrangement of these molecules into series of building blocks. It's called as polymerization. Further, what degree of polymerization it is becoming, based on that it is also defined as polymer degree of polymerization. Now you can see the chemistry and structure of polymers. So here, for example, I have been taken the polyethylene as a material to just for simple understanding of the chemistry behind this. Now you can see the tetrahedral arrangement of carbon and hydrogen. So all these are carbon molecules and the smaller one is the hydrogen molecules. Now you can see one carbon molecule is surrounded by two hydrogen molecules. So that hydrogen molecules is repetitive in nature. You can see this is a carbon and these two are the hydrogen molecules, and it is being repetitive in blocks or the numbers. So this n number of series where it is get connected to the carbon molecule. So you can see here this is carbon molecule and the hydrogen molecule. A series of these hydrogen surrounded on the carbon, so which is repetitive in nature. So polyethylene is a long chain of hydrogen and carbon, generally it is called as hydrocarbon. So this figure indicates the repetitive units and the chain structures, and this is the backbone of the structure. So chemically it looks like this, and just for representation it is written like this. Okay, so this is what the polymer and the chemistry and structure of the polymer. Now you can see the polymer is not a new material. It has been very old, and but all these are natural. These ancient polymers are also called as natural polymers. So these polymers can be called or defined into two ways. One is the natural polymers and the synthetic polymers. So whatever these present day polymers we are using, all are the synthetic polymers, or which are also called as artificial polymers. So these ancient polymers are also called as the general or a natural polymers. So these natural polymers are extracted from the plants and animals. Okay, so these are got from the wood, cotton, leathers, rubber, wool, silk. So you can see this in olden days. Okay, so they used to play with make the material with the polymers. All these are natural polymers. So the oldest known polymer is the rubber balls used by Incas. So you can see here the balls which they are using, when it hits the wall, it repels back. So it bounces back. So generally used natural polymers are nothing but the proteins and cellulose. And these are also called as the glucose and cellulose. So this is the glucose and that side is the cellulose, which is generally observed in the cotton. So this is the cotton. In that you can get both glucose and cellulose. Okay, so in this you can see you can get the 70% crystallinity. So generally the metals are having 90 to 95% crystalline. No, so these are the up to 70% crystallinity is having. This is found in the cotton. So these these are cotton is also serves along with the treated wood pulp as the source, the industrial production of cellulose derived material, which were the first plastic materials for commercial importance. So this has been started in a wild olden days, but it was not that popular as of the modern day polymers. So this you can well known thing, that is rubbers, elastomers. So this has been generally extracted from the plants. Okay, so even in the olden movies you would have seen the extraction of rubber from the plants. So this is a natural rubber where the glass transition temperature is -70 degrees, and it did not become a generally the useful up to mid 19th, because many people were not aware how to use this rubber material for what type of applications. Hence it was kept or it was lagging back only. But in the mid 19th century, when Charles Goodyear found that heating with sulfur, a process called as vulcanization, greatly we can improve the characteristics and properties of the rubber material, particularly this material, and they started using this for the tires. So hence this rubber, okay, started getting more importance after discovering the vulcanization process. And the first vulcanization process, the application is the tires for vehicles. Okay, so this is how after heating the chemical structure changed, and it is called as cis polyisopropylene propene, and then it started converting for the tires, and then it started gaining more and more popularity. So these are some of the articles which are found in the frontiers of the polymer science. So if you are interested, you can go here and download the papers and for higher additional knowledge. So next is the hydrocarbon molecules. So basically, generally all these polymers are based on the arrangement of hydrogen and carbon. And depending upon the type of polymer, a little bit changes will be there, like chlorine or a material which have been added. So many hydrocarbon molecules is nothing but the arrangement of carbon and hydrogen. So these many organic material are hydrocarbons composed of hydrogen and carbon. Most polymers are made up of the hydrogen and carbon, generally known as hydrocarbons. The bond between the hydrocarbon molecules are covalent. Okay, so this is very, very important. So these are covalent bonding. So each carbon atom has 4 electrons that may be covalently bonded. The hydrogen atom has 1 electron for bonding. So a single covalent bond exists when each of the 2 bonding atoms contribute 1 electron. Example, the methane, CH4 is the one of the best example for the bonding between the hydrocarbons. So next is the saturated hydrocarbons. So each carbon, so you can see methane, ethane, propane, butane, pentane, hexane, all these are the saturated hydrocarbons. So these are the composition CH4, C2H6. Okay, so the molecular structure is also there, and the boiling point of each one is also given in front of that. So these are the general purpose, the saturated hydrocarbons, where you can see the melting point is -164 degrees, okay, of the methane. So propane is -42.1 degrees. So each carbon has a single bond to 4 atoms. The 4 valency electrons are bonded, the molecule is stable. So examples are seen in the table. The covalent bonds in each molecule are strong but only weak in hydrogen, and the van der Waals bond exists between them, the molecules. Okay, so here the important is the bonding between the hydrogen and carbon. So these are weak in only the arrangement at the hydrogen molecules here, or else rest of it is fine. So most of these hydrocarbons have relatively low melting points. So however, boiling point rises with increasing the molecular weight. Suppose in this, if you are going to increase more number of molecular weight, then the melting point also increases. So these are some of the examples of unsaturated hydrocarbons. So double-lined triple bonds. So there it is covalent bond, here it is double-lined. Triple bonds are somewhat unstable, involve sharing or 2-3 pairs of electrons repeatedly. So they can also form a new bond. So double bond is C2H4. Now you can see here there are 2 carbon molecules and 4 hydrogen molecules. So a triple bond, so you can see here the bonding is triple and this is acetylene. So ethylene and acetylene. So there those are methane. So this is ethylene and the acetylene. So here C2H4 and C2H2. So these are isomerism. So isomerism, 2 compounds with the same chemical formula can have different structure, but the atomic arrangements, for example, C8H18. So this is the normal octane. Okay, so octane means 8. So you can see here 8 number of carbon molecules and 16 number of the hydrogen molecules. So these are repetitive in nature, you can see here. So hence this is having CH3, rest is up to this, it is CH2, 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 and the last one is again CH3. So this can be further reduced to CH3, H3C and C2H because it's repeated in nature, and this is last one. So further it can be written like this. So they are having the same formula, same composition, but can be represented in a different order. Okay, so this is normal octane, this is dimethylhexane. So this is how the chemical structure changes of a same material, which is called as the isomerism. So this degree of polymerization is done in 2 ways, that what we have seen in earlier, that is the additional polymerization and the step polymerization. So here the addition polymerization is the initiation. So the bonding between 2 monomers, so how that bonding should happen. So what is the deciding factor? So that initiation of that bonding is developed by the addition polymer. So this is the catalyst where it is initiating the bonding between the carbon molecules, carbon and hydrogen molecules. So this is called as addition polymerization. Okay, so any polymer has 3 things, that is the initiation, next is the propagation, and next is termination. So this propagation is nothing but, so this is a single monomer. So this single monomer, if you want to convert it to polymer, the catalyst has to give a initiation. So after that it increases the polymerization, that is called as propagation. Then this propagation has to end at the end, so that is called as termination. So this termination is of 2 types again. So the disproportion and the combination. So this is a type of addition or a chain polymerization. So next is the condensation or the step polymerization process. Now you can see the 2 different polymers. So this ends with hydrogen, this is hydrogen. So both are mixed, and you are going to get the result of this is combination of the hydrogen and oxygen, that is H2O, that is water. So this type of application is used for the nylon. So hexamethylene diamine is combined with adipic acid, so that gives result to nylon 6 or PA6. So this is polymerization process. The free radical polymerization ethylene gas reacts with the initiator catalyst. That is R is nothing but the initiator catalyst for the unpaired electrons. So this is the initiation, then it is propagation. So monomer refers to a small molecules from which a polymer is synthesized. So So from this synthesization, the propagation happens. So these are nothing but the monomers which are turning out to a polymers. So these are some of the common addition polymers. So polyethylene, again this polyethylene is classified into two types, low density and high density. Polypropylene, polyvinyl chloride, again polystyrene, polychloride. So all these are applications of the addition polymers. Okay, so the further the property is also given and the uses is also given. So the polyethylene, maybe the low density or high density, is used for soft, waxy solid, rigid and transparent solid. So the application of those are the film wraps, the plastic bags, electrician insulation, bottles, toys. So like each material is given with its particular application and the properties. So we need to select the what material we require for what type of application. So we need to come in the reverse order. So these are some of the examples of the condensation or the step polymerization process. So the polyester, okay, so polycarbonate, polyamide, polyurethane, all these are the step condensation process, and these are sometimes these can be also taken as the thermostats and earlier one as a thermoplast materials. Now let us come back to this polymer molecular weight. So this molecular weight is nothing but the weight of the molecule. So in a given volume, if the more number of molecules we can fit, then the property and the density and the characteristics of that polymer increases. So because of this increase in the molecular weight, the application also changes. So that is why we have seen in the earlier case, that is the low density molecular weight and the high density molecular weight, though both belong to the same category, because of the difference in the molecular weight or the density, the application of high density polyethylene is wide variety compared to the low density polyethylene. So here this is having the low molecular weight and this is having the high molecular weight. So you can see here in the high molecular weight we can fit more number of molecules in a given space. There you are having the less number of molecules in a molecule chain. So polymers can have various lengths depending upon the various number of repetitive units. So more the length, more the repetitive units, smaller the length, lesser the repetitive units. So during the polymerization process, not all chains in a polymer grow to the same length. So there is a distribution of molecular weights. So you can see each material cannot grow up to that length. So in between they get cut. So there are several ways to define a average molecular weight. So the molecular weight distribution is a polymer describes the relation between the number of moles of each polymer species and the molecular mass in that particular species. So how many number of molecules are there, and based on that the molecular weight or the molecular mass also changes. So this is the molecular weight distribution. You can see the average number of molecule numbers and average weight of molecular weight. So here Mn is nothing but the number of average molecules weight, that is mass. This is mean middle molecular weight size range, and Xi is the number of fraction of chains in size, and weight fraction change in size. Okay, so this gives your molecular weight. So based on this molecular weight, the property is decided. You can see here when the molecular range is in terms of 5,000 to 10,000. So the mean molecular gram per mole is 7,500. So the Xi is 0.05 and Xmi is, that is standard mean deviation is it. So these are the fractions, so molecular weight. So this is having the small molecular weight and the larger molecular weight. Because of this, the property also changes. So this arrangement of molecules will give the degree of polymerization. So what degree of polymerization? It is nothing but the process of polymerization, that is either the step or the addition. So more number of polymers, polymerization, better the properties of the polymer. So this M is the repetitive molecular weight and the mean molecular weight. This is for a simple example of PVC metal, that is polyvinyl chloride. So C2H3 and chlorine. So this molecules is two carbon molecules, three hydrogen molecules and one chlorine molecule. So a PVC material is having C2H3Cl. It means that two carbon molecules, three hydrogen molecules and one chlorine molecule. So if it is repeated in this, then it is called as polyvinyl chloride. So this is the molecular weight, the carbon, the carbon molecular weight, hydrogen molecular weight and the chlorine molecular weight, and all together it will be 62.496 grams per mole. So this is one PVC molecular weight. So here degree of polymerization process is, so the mean is 21,150, so divided by this gram per mole, and the degree of polymerization process is 338.42. So this is how, this is just a simple example is given to calculate the degree of polymerization process. Here we have taken for example is the PVC material. Similarly, you can take it for the polyethylene, polypropylene, polystyrene, nylon, like that. So only thing you need to change this material. Accordingly, you need to change the chemical structure. According to the structure, how many molecules are there, that you need to take it. Okay. So this is how you need to calculate the degree of polymerization process. Next is the polymer chain length. So many polymer properties are affected by the length of the polymer chains. For example, the melting temperature increases with increase in the molecular weight. So if the molecular weight increases, then the material becomes harder, and the boiling point, the melting point also increases. Hence, you can't get the uniform length. So because of this increase in the temperature, so either it is length is more or the length is less. At room temperature, the polymers with very short chains, so it varies from roughly 100 grams per mole, so will exist in liquids. Now at high temperature, so it is those with the weights of 1000 grams per mole are typically waxy solids or soft resins. So next it is having the range of more than 10,000 to millions. So solid, that is solids are having more polymer chains, so greater than 10,000. But in those with semi-solid, it is up to the 1,000. Then in liquids it is 100. So 100 or less. So like this, the polymer chain length varies in the three sectors. So that is less than 100, the liquids. So up to greater than 100 and less than 1,000, that is in the semi-solid form. And greater than 10,000 to any millions or lakhs, then it is in a solid form. So this is dependent on the temperature. So the molecular weight affects the polymer properties with examples of these are elastic modulus and strength. So we know that the elastic modulus or strength of liquid is less and the elastic modulus of semi-solid is little bit greater than semi-liquids and but less than solids, whereas the strength of solid are better strength as well as the high elastic modulus compared to the semi-solid and the liquid conditions. This is polymer molecular shape. So you can see that the angle is 109 degrees, so that is repeated in nature and it keeps on changing. So straight, that is figure B, and twisted is C. So chain segments are generated when the backbone carbon atoms, these are the black circles, these are the carbon molecules, okay, so are oriented in the figure. So the chain bending and twisting are possible by rotation of the carbon atoms around their chain bonds. So some of the polymer mechanical and thermal characteristics are a function of chain segment rotation in a response to a applied stresses or the thermal variations. So if the bonding between the carbon and hydrogen, if it is a linear, then it is a copolymer. If there is a twisting of the rotation or the twisting of the carbon molecules, then the next series will change, though the chemical composition is changed. So this change in the arrangement, that is the twisting or the bending, will leads to change in the properties. Those properties are these thermal and mechanical. In mechanical, the stresses will change, and in thermal, the thermal vibrations are going to change. Because of this, either the metal will transmit more heat or it absorbs more heat. So it doesn't allow the heats to flow. Again, that is dependent on the molecular weight. So this is chain end-to-end distance. So now you can see all these the arrangement of polymers. So this is like a entire the ball which the size is bigger but the distance is smaller. In this, if it is dispersed and oriented in this, so this is the radius. Now you can see this representation of a single polymer chain molecule that has a numerous random kinks and coils produced by a chain bond rotations. It is very similar to a heavy tangled fishing line. So this R is the distance between end-to-end distance of the polymer chain, which is much smaller than the total chain length. So in that, though the chain length is more, but it is condensed as a roll. But here the chain length is the more. These are molecular structure of polymers. So as in earlier cases we have seen, this is a bonding, secondary bonding. So these are linear, these are branched, these are cross-linked, and these are network. So in each type of arrangement, the chemical bonding is different. As a result of that, the strength and properties are also different. So the physical characteristics of a polymer depends on the differences in the structure of the molecular chains. So other variables are shape and weight. So the strength of the polymer cannot be just decided on the arrangement of the chemical composition of the hydrogen and chlorine or a carbon. So it also depends on how it is arranged, okay, and what shape it is arranged, in what degree it is oriented, and what is the weight of that. So based on these, the physical characteristics, okay, the mechanical characteristics and the thermal electrical characteristics will change. So based on this, we can see the linear polymers. So linear polymers have repetitive units joined end to end in a single chain. There may be extensive van der Waals and hydrogen bonding between the chains. Example for the linear material are polyethylene, the PVC, nylon. All these are the linear. So next is the branched one. For the branched one, so these HDPE, LDPE, so these are the branched one. So you can see where the side branches chains are connected to main chains. These are termed as the branch. You can see these are termed as the branches. Branch polymers, linear structures may have the side branching. So the examples for this is the LDPE and HDPE. Greater chain linearity and chain length tend to increase. The melting point will improve, and the physical and mechanical properties of the polymer increases to the greater crystallinity. Next is cross-link. So these are the cross-link, and the examples for this, the rubber material. Okay, so these are the network material. Small molecules that form a 3 or more active covalent bonds create structures called a network. The polymer, this is the polyurethanes, and the epoxies are the application of the network polymers. Okay, so again these epoxies are most famous for this bonding and for the framework applications. So next is these polymers are again subclassified into thermoplastic and thermosetting polymers. So we'll see about this thermosetting and thermoplast materials in the next class. If you have any difficulty in understanding these up to what we have discussed till now, you are free to ask the questions and I will respond to you all. Okay. So thank you.